hours. The 3,200 man hours have been wasted here.
Absorb it and I try to implement it. So yes, in a way, so and I always say that whenever he wishes, the Guru wishes, then I will.
Usually, when we start a survey, geophysics is looked at as a tool. For a geologist, they start with a different notation of mapping, trying to understand the lithologies, the contacts, and then the question of geophysics comes. Preliminarily, the four-stage formula has been used in our investigations. In the stage one, if we look at the preliminary information is about collecting the geological maps, preparing the digital elevation maps, and how the preliminary information which has been gathered, what type of geophysical technique is useful for that. And then generation of the synthetic models, trying to understand using different iterations for the investigation of our interest. Stage 2 is about the integration of these surveys. How the integration is done and what types of techniques have to be used for the mineral targets. And then trying to understand from the technique response from the barren zone to the mineralized zone, and the validation of the data using the borehole data, and the final is the fingerprinting of the geophysical anomalies. Then stage 3, consolidating the values from the stage 1 and stage 2, trying to understand the test drill holes to validate this data. In the stage 4, documentation of all these 3 data sets and trying to develop the models and validate with the third dimension, that is borehole data. This is the same slide I just wanted to give in a table form, like the literature survey, mapping, selection of the geophysical methods, data processing, geological modeling, and ultimately the decision making. As I gave you the background in the preliminary stages in the few back slides, the stage 1, we have taken a test example from Sukinda. Sukinda, as you most of you know, is the world's 4th largest chromite mine in India, and most of the surface chromite rich pockets have been exhausted. So the need to go deep and also to find the high-grade chromite is the need of the hour, and it is also declared as a critical mineral in the Indian recently released critical minerals list. So this mineral is of prior importance for the nation and also for the different types of sectors in the industry in India. So we have taken an example from the Sukinda, trying to find out the extensions of these chromitite bodies toward the south of the Sukinda chromite belt. So we have taken we had test boreholes towards the south of the area. We had something like 16 boreholes available, and the data was available. We have taken the stage 1, how it is done. A borehole data will have a lithological control. So using that lithology, the synthetic models have been developed. As most of the geophysicists know that chromitite is a very difficult to target because of its associations lithologically. It associates with the pyroxenite, peridotite layers. It also associates as layers continuously embedded with other lithologies. So the response of the geophysics is always the response you get from the respective rock type. For example, if you have magnetite, you get magnetite associated with the chromitite. So the response would be to nullify the magnetite lithology and take the chromitite. So it's like a very difficult situation to find out the thickness of the chromitite bands and what types of exactly techniques have to be. Routinely, gravity magnetics, electrical ERT have been used, but the success rate was, not to the extent where it has to be. So once you develop the synthetic models, we exactly know how to nullify the actual response of the chromitite from the associated rocks. In the stage 2, as you see toward the left of the slide, the field Google map where the cut path actual area has been studied. So there were 3 old pit mines named at Quarry A, B, Quarry G, and also Quarry H, and there was towards your right side the Dhami. And towards the right side, if you see, using the data generated, we developed the models using gravity, using magnetics, and also depth persistence, and trying to iterate and cross-check with the borehole data what is available. In the stage 3, we have used residual gravity, residual magnetic anomaly, and try to understand the actual mineralized portion. Stage 4, we develop the responses and ultimately the 3D geological model, and also the fence diagram for this study area. So the topic of today's interest is using different techniques like gravity, magnetics, ERT, EM and GTR. What is the cost per kilometer analysis? In our experience in Sukinda, when we do it, so gravity is 12,000 rupees per line kilometer. Magnetics is very less. As you go on, the price cost increases. And this includes all sorts of topographical surveys, labor cost, the man days, etc. This has been taken from a scientific paper. I just wanted to give you a gist of what is actually the things. When you do different surveys, the time factor versus the response and the amount of the cost when you do it. So the geophysical techniques play a crucial role in the planning of the exploration projects, from the initial, the middle stage, and the final stage. For example, in this particular table, I would like to give you an essence or the summary of the entire talk. The chromite was the target for our mineral investigation. This was the preliminary, then the chromite in the middle term planning, and the chromite for the strategic term planning. And what are the techniques we have used? When we take time days, for example, all these techniques in the preliminary stages don't take more than a week. And the depth is almost 120 meters. And the cost, if you see, is somewhere around $20 US. Drilling, as you go, the depth is same, but the cost has been increased by 3 times. When you do the middle term planning, The same techniques, more time, more depth, and also the price has increased by 3 times in the drilling. So what I mean to give in this slide is, geophysics has a critical role in the initial stages of the planning, middle-term planning and the strategic planning. So the cost plays an important role when you want to invest the money for the drilling. So take the data from the geophysics and plan it nicely, then the project will be of utmost importance. See, I will leave it to the audience for these conclusions, as the time is very less for me. But the summary I would like to tell you is, the geophysics gives a true picture to give about the uncertainty of the geological uncertainty can be reduced, and also can we use the data set with the accurate modeling for the strategic, tactical, and also the operational mine planning and promoting the high productivity. So the integration of these geophysical techniques is cost effective with comparison to other high-end techniques where you can take the data for the mineral investigation. Thank you for your patience.
There is a big potash deposit. Initially, actually in 1973 work was started there, but without identifying which parameter to be done in geophysical logging to identify potash bands, they took only gamma probe, just thinking that we will receive a high count. But clay also and galvanic sandstone also give high counts, but later on it is understood that we have to take more logs to identify all the potash minerals in this halite deposit. So potash is a sedimentary deposit. It has different minerals in same sequence. They are halite, sylvite, carnallite, polyhalite, lampenite, and insolubles are also dolomite, gypsum, anhydride are also present. Mostly potassium chloride is economical mineral and other polyhalite. But at the bottom generally dolomite, then limestone, then anhydride, then polyhalite, and then sylvite, then carnallite. The sequence of deposition is like this. The objective was to identify only the potash bearing zones, because earlier they do only gamma, but gamma in clay also high and in galvanic sandstone are also high. So they calculated huge results, but actually it was not like this. So later on we done multi-parametric geophysical logging in which we adopted density and spectral gamma, then neutron along with dual neutron, and then resistivity. So why spectral gamma is selected? To differentiate counts coming from potassium, uranium, thorium. Because if you are doing only gamma probe, then cumulative counts you will receive. So you will not be able to identify whether counts are from clay bands or from shale or from polyhalite. So to differentiate, we done spectral gamma so that thorium, uranium, and potassium counts will be separate. And then we done calculated percentage of this potash. Actually, international formula is correct gamma counts means total counts minus background counts multiplied by factor, that is 0.0562344.5 inch boron. It is international, but for our deposit, this factor came 0.04142. That is corrected gamma rays multiplied by this factor, you will get percentage of K. And it has 99% calibration with our chemical analysis. So what percentage came from chemical analysis, it is completely matching. So that then we done density, because all the minerals they have different densities. Suppose the anhydride and polyhalite they have same density, so you cannot differentiate it by density. So we will take the help of neutron, because anhydride is hydrogen index is 0, but polyhalite hydrogen index is more. So in polyhalite you will get low gamma, low neutron count, and in unhydrated you will get high neutron count. So these two minerals, unhydrated is also present with polyhalite. So we differentiate them with density probe. Then we done neutron. Neutron also helps to that which potash band is hydrated and which is non-hydrated. If you will not do neutron to identify potash minerals, it will be very difficult because half minerals are hydrated and half are unhydrated. In hydrated you will get a low neutron count, and in unhydrated you will get a high count. So this density and gamma, when you will do this cross plot, so easily you can identify mineral from density as well as from gamma counts. And this is cross plot of density and hydrogen index. Then electrical is also must in potash. Otherwise you will not be able to identify clay and these potash zones. Because resistivity is low and clay is there, and otherwise in all potash you will get high resistivity. So these are different minerals I have given in a tabulated form, their formulas and their physical properties. Because until and unless you don't know the physical properties, you cannot adopt accurate methodology. So here these are logs present where we have identified all kyanite, halite, silvite, all bands has been identified. What geophysical help you take sampling there only where you are getting high gamma counts, low neutron, and you can check density also. So there is no need to do sampling of a whole boron. So like here also that polyhalite, then that big one band is halite. There are no gamma counts high in halite. Halite is sodium chloride and silvite is potassium chloride. So likewise we have identified all the bands where is polyhalite, where is silvite, where is carnallite, where is langbeinite, so where is anhydrite, where is dolomite. So all the minerals we have identified with the help of geophysical logging, but we have to take at least 4 parameters. With 1 or 2 parameters you cannot identify. So this is also same anhydrite. In anhydrite you see the resistivity is high and the natural gamma is low and density is 2.8. Now generally polyhalite and anhydrite they are side by side. So their density is same 2.9. So from density you cannot differentiate them. But one is hydrated, another is unhydrated. So you have to take the help of neutron law as well as gamma also. So these are all field examples from the boron. This is field data in which we have identified all the minerals. Around 20 minerals are present in a potash origin, which is around 300 meter in thickness. Total zone is halite, but within that halite around 20 minerals are there. So those minerals we have identified with the help of geophysical logging. So this is also from the field. So many examples from the boron I have taken, in which silvite, halite, all minerals has been identified. This is also from in the same area, another boron. So like this. So depending on physical properties, here also you see that anhydrite, you see resistivity is high in anhydrite, and then natural gamma is 0. And this neutron will be high because it is unhydrated, and density is also high. And if you see that spectral gamma, you see that all potassium, thorium, uranium, they are 0. So depending on these parameters, we have identified all the minerals separately. So we studied their physical properties and identified which are hydrated, which are non-hydrated. So we took the help of all parameters, and accordingly we identified all minerals in a potash band. If you think with 1 or 2 parameters you can identify, it is not possible. So in addition to this parameter, one more parameter sonic logging also we can take, because in potash minerals that velocity of P wave is also separate. So if you are still facing problem with 4 parameters, you can take sonic. It will help you in identifying these potash minerals. So thank you.
We have the next presentation from Mr. Deepak Maurya from GSI, who will be presenting his work on gravity and magnetic appraisal of the SandurSuperTerrane, Dharwar Craton, India, for shallow crustal architecture and mineralization.
So today I am going to present about my work over Sandur system, that is also known as SandurSuperTerrane on gravity magnetic. So talking about Sandur system, the Sandur system is one of the old occupied in one of the oldest terrain, that is Dharwar Craton, and it is well known for its economic deposit of iron and manganese, and simultaneously it holds a unique position among other systems of Dharwar Craton. It occupies in a closed granite belt, and it preserves the lithologies which is commonly present in both the Western Dharwar Craton and Eastern Dharwar Craton system. And the Mankamba et al. In 2008, he described that the sixth belt is accreted along the Sandir Valley discontinuity and Suglama Devikonda discontinuity, and he named it SandurSuperTerrane. That's why I written name SandurSuperTerrane. And we have used NGPM data, which is on 1 milligauge, and magnetic is 150 nanotesla, and in the station spacing is about 1.5 kilometer. So this is this is the geology map of the study area, and this one is the key map. In key map you can easily see that there is a 400 kilometer long closed granite belt. Within that there is a Sandur system belt. So coming to the geology, here in geology, Sandur is comprised of mainly 2 rocks, that is metavolcanic and metasedimentary rock. Metavolcanic is composed of mainly the volcanic, acid volcanic, amphibolites, like that. And metasedimentary is composed of DIF, argillite, and limestone, dolomite, this kind of rock. And in our area, I have selected some other systems, that is the Chaturvedi system, and one is Chaturvedi system. But my focus is on mainly the Sandur system. And we have also collected some rock samples also. So this is the Google anomaly map. Here we can see that the blue color inverted triangle is the rock sample location, and other is iron, manganese, and gold deposits, which are already known. And overall we have seen that the gravity high observed over system, and there is a low. This low, and this low is observed over clay-squared granite, and the moderate values are observed over peninsular masses. But however, we can see that there is a one high and this one high, GS6 and GS7. 3 highs are observed over close-squared granite. So we are interpreting it is either the system belt is present below the close-squared granite, or it may be the magmatic underplating. And we have also observed a steep gravity gradient along the contact of the schist belt. This may be due to vertical or subvertical contact of the schist with granite and ices. So coming to magnetic, as the area is low latitude, it is very difficult to interpret it. But however, we try to interpret it. So in magnetic anomaly map, we can see that there is a very strong bipolar nature of magnetic over the schist belt here. And this anomaly is around 3,000 to 4,000 nanotesla. And after for its interpretation and better purpose, I have transformed it, reduced to equator then we can see that there is some symmetrical anomalies are observed. But however, due to remnants effect, it is not clearly bipolar nature is gone. And I have also plotted analytical signal map of this. And in analytical signal, we can clearly see that there is over the cyst belt clearly high magnetic, high analytical signal is observed. So over the peninsular leases and close-bed granite, there is a subdued nature of magnetic anomaly is can see. And most of the east-west trending dike we can observe easily here. But north-south striking dike is not observed because it is in lower latitude is magnetically invisible. And coming to the next is petrophysical analysis. We have collected 106 representative rock samples from the Central Cyst belt, and in which we have analyzed the density and susceptibility values, which I have plotted density against susceptibility value. We can here easily see that the peninsular gneiss rock are mainly non-magnetic or low magnetic, having low magnetic susceptibility. And however, we can see that over the close-bed granite there is a low magnetic is comparatively peninsular gneiss magnetic is comparatively high. It may be due to higher biotite content or something else. And over the quartzite, we can see that there is a negative magnetic susceptibility. And next, coming to the metavolcanic rocks, these are we can see that metabasalt have a comparatively lower susceptibility, and only BIF have which have the highest susceptibility value, which maybe that is the reason we are getting a strong bipolar magnetic signal over the cyst belt. And dolomite dike has also higher value. And next is the spectral analysis of gravity and magnetic data. In gravity data, we can see that maximum depth is obtained over 7.26 km, which we are interpreting that is the maximum depth of Sandur cyst belt, and second interface we obtained at a 2.80 km, which may be due to the other volcano sedimentary terrain or other cyst belt line, and some these Sandover values are due to the basic or mafic intrusive. Next, coming to residual and residual gravity map. In residual gravity map, we can see that there is alternate band of highs and lows. In general, this positive residual gravity is associated with volcano sedimentary sequence, which we call also cyst belt, and these lows are observed over close-bed granite. And in regional gravity map, we can see that the positive source of the anomaly is very deep. Either it is a crustal level, mid-crustal level. And next, we derived the first vertical derivative of total height and gradient of gravity data. In first vertical derivative, we can see that all the structural features clearly observed, and most of the mineralization like this it is observed over a high first vertical derivative, and in total height gradient map, we can see that there is the Sandur cyst structural disposition and structural disposition of Chaturvedi system is completely different. It is like a basin form in over the Sandur system, and it has and we can clearly see that the contact is clearly highlighted. I have plotted Euler solution for the structural index of 0.5 for gravity data, and we can see that the contact is mainly 1 to 2 km, and over the mineralization it is also 1 to 2 km. Next, coming to the modeling, gravity and magnetic modeling. In gravity and magnetic modeling, we can easily see that the maximum depth of Sandur cyst belt is 7 and other cyst belt like Kusteki and Chaturvedi cyst belt, which have depth It is the only Chittoor some part of system is in my area. So what depth I have calculated is that is 3 to 4 kilometer, and the route of the intrusive granite is 2 to 4 kilometer. And we can easily see that the central structure, which is very narrow, but the depth is around 7 kilometer. And now coming to the conclusion part. In conclusion, we have said that the central structure have deep troughs of geometry, and the gravity and magnetic model has indicated the 7 kilometer depth of central system and 3 to 4 kilometer depth of adjacent system. And we have another topic, mineral is also there, that we have demarcated mineral processing zone in a over residual gravity map. It is based on presence of gravity gradient and nozzling, high residual gravity and high magnetic gas signal. And the Chaturvedi shear zone and one shear zone I have already informed that has a high magnetic signal and gravity gradient. Thank you.
Next presentation from Dr. Bangaru Babu from GSI, who will be presenting his work on geophysical evidences of concealed East Coast sedimentary basin, Kavali Nellore areas of Andhra Pradesh. Dr. Bangaru Babu.
Here I want to present my field data result in front of geoscience community. Thank you for EAG for giving the opportunity to present my data set. Today I am going to present my geophysical results carried out with geophysical surveys carried out in part of the Nellore Kavali area of Andhra Pradesh. Today I am going to present my talk on geophysical evidences of concealed East Coast sedimentary basin, Kavali Nellore area of Andhra Pradesh, South India. This project we are carried out on the project of National Geophysical Mapping Program of Geological Survey of India. So we have covered around 3 deposits in the east coast of India. So these are my co-workers along with me. Today I am going to cover geology of the part of geology and geometry of geophysical surveys, methods and processing and interpretation results, what you are got from this survey and the conclusions and results. So this is the survey area. We have covered 3 deposits, Survey of India deposit, N by 13 and N by 14 and by 15. So these are my station density map. So we are taking utmost care for distribution of the gravity magnetic stations. It is equally distributed all survey areas. So this object of this survey is to generate the Boger gravity map and IGRF corrected magnetic anomaly map. After generating these maps, we have to identify the mineral potential zones by applying the series of corrections to this data set. So we are collected the gravity magnetic observations at 2.5 square kilometer one area. Around 875 gravity magnetic observations are collected. So we have used CG5 gravimeter and GEM total magnetic magnetometer and LICA differential global positioning system. We are taking utmost care for collecting the quality of data set in field work. We are taking repeatability. We are getting gravity illegal 0.03, 0.05 illegal in gravity and 10 to 15 nanotesla in magnetic survey and 20 to 30 centimeter difference in elevation. We are getting repeatability. So before starting our survey, we are established on gravity base, IGS and gravity base and to area. By using this gravity base, we have collected we have covered the entire 3 deposits by using this gravity base. So this is my field photographs. We are taking the utmost care in field work. We have selected a field stations which is free from the cultural noise and electrical lines, all these things. So we are taking noise-free area for collecting the gravity and magnetic data sets. This is the DGPS control station. We are taking the benchmark near to the railway station. By using this DGPS benchmark base station, we are moved with the rover with gravimeter. So this is my gravity base established near Nellore area inspection bungalow. So this gravity base we are tied with one more IGS and gravity base near to Gudu area in Andhra Pradesh. So this is the geology of the present area. Totally this present area is located east coast of India. It is eastern part of the the Kadapa Basin, eastern part of the Kadapa Basin. This is mainly, regionally this is the protozoic eastern Ghat mobile bed occurs in the east coast portion of the prominent consists of the Archean Dharwar Craton. It is overlaid by the protozoic segments along the east coast and bordered by the Bay of Bengal. The area exposed to the rocks of the EGMB and supercrustal rocks of Nellore cyst belt of Archean and Megamotite gneiss. Peninsular gneissic complex of Archean and intrusives of Mesoproterozoic age. East coast Gondwana and of Jurassic age located in this present area. And Rajahmundry sandstone occurs over the geographic area of the eastern part of the Bittergunta and Kavali areas. This is somewhere Kavali, Bittergunta is somewhere here. A thick blanket of quaternary alluvial sediments occur in the peninsular Penna River. This Penna River is extending, cutting across this present area. This is the location of the Penna River. The quaternary sediments are classified into Puchireti-Palyam and Penna formations. Puchireti-Palyam is one of the paleo channel deposit which is formed by the silty clay and by coarse grain, and Penna formations has flood grains deposits located in this present area. Here, gneiss of PG trends are trending in north-south directions vertically and subvertically towards the east. Quaj and cyst rocks of the Nellore cyst belt is located in the western part of the present area. Nellore cyst belt rocks are introduced by the Megamotite gneiss. This Megamotite is well exposed around the Kusumur area. This is somewhere in Kusumur area. This is the location of the Nellore cyst belt. So NSP and associated rocks are trending north-south direction and north-northwest to south-south to east, dipping dips on either side of the present study area.
So now I invite Swati from NRC for presentation of his work on delineation of basement structure of alluvial megafans using satellite gravity and multi-spectral data.
And audience present here. I am Swati Singh. I am a geologist working in NRC on mineral exploration and quaternary studies. I find that the topic of my talk is not as per the session's theme, but it is a very interesting work which I have done for the quaternaries, and it has an application as well on the mineral exploration. So I proceed with my presentation. The topic here for my talk is delineation of the subsurface structures in the alluvial fan using geophysical data. So basically I will be talking about the depositional system in the Himalayan region, which is in the form of alluvial fans. And as we know that these fans have been affected by the geological as well as the climatic conditions. And these depositional landforms are very vital for the evolution of the foreland basin. In case of Indian subcontinent, it is the Indo-Gangetic plain, where this fan plays an important role. So it is very important to look into the alluvial fan, the mega fans in this area. So the significant effort have been made by various researchers to study fan-wise depositional setups for Yamuna Ganga, Gandhar, Kosi, and many other mega fans. But the gap lies where there is no detailed investigation done to understand the subsurface structures or the basement structures which affects the alluvial deposit in this area, and how it is regulating the framework, the depositional framework at large. So here this satellite-based geophysical sensor can provide us the regional details, and which is a prerequisite for this kind of subsurface structure, understanding of subsurface structure affecting the alluvial system. So the basic objective of the study was to demarcate the alluvial fan using optical and SAR satellite images, and to delineate the subsurface basement structure using the gravity data. And then to relate these structures using the surface imprints using this upward continuation technique. And then there was an intercomparison done between the fan areas to investigate the structure, the fan which is structurally controlled or it has a climatic control. And then we have identified some high synergistic hotspots where we have done, where the tectonic process was prevalent, where we have done some GPR survey. So this is the area, this is the entire Indo-Gangetic plain, the Piedmont zone, where all the fan system is there. To the audience, it is well understood that the fan is a triangular deposition unit which is formed by the sudden break in the slope and the river dumps or deposits its sediments. So we have taken some 5 mega fans in this area to understand the subsurface structures and its imprint on this fan region. So the data utilized for the study was the optical data, where we have tried to delineate the area or the extent of the fan using the Sentinel and ANSWER data. The microwave data has also been complemented with the optical data to understand the extent of the fan region, and then the satellite geophysical data. It has been the IRIN 64 has been used for the study. The IRIN 64 is a static global gravity field model which is developed in combination with the ground-based information as well as the satellite-based gravity data from GOES-GRACE satellites, and it has a resolution of approximately 10 km. It's a gridded information. So it was being primarily used for the study, and the field data was collected in the hotspot region, and we have done the GPR survey for that area. So these are some of the sources from where we can get the data. Like from Guniti we can get the optical data. From ICGEM we can get the IRIN 64 data, and GSI Bhokosh also hosts some ground geophysical data, and other ancillary data were used like topography, GPR and microwave data. So the methodology adopted for the study was, first of all, the satellite data was multispectral and SAR data was used to delineate using some image processing and image transformation technique. We have delineated the extent of the fan region in this area, in the entire Himalayan region, where the 5 fan boundaries were being delineated. And then the satellite gravity data was being processed to extract the Booger gravity anomaly, and then the regional separation was done, and the Booger gravity derived products like basement depth and grid derivative was derived. And using this upward continuation technique, we have tried to delineate the subsurface features and the basement structures, and integrating the fan region and the basement structures, we have tried to identify some of the areas or extent where the tectonic expressions are there along the fan, and for those areas the GPR survey was conducted. So this is the Booger gravity anomaly, and the basement depth was derived. As you can see, there are the areas near the Kosi and the Tista fan where the high basement depth was being identified. The thickness of the sediment was high, and the tilt derivative is the ratio of the vertical to horizontal derivative. It tells us the contrast, the high to low contrast of the tilt derivative tells us about the structure. So if we see, the structure also are more extensive, more indicative of the tectonic prevalence towards this Kosi and Tista fan region. So it was further interpreted to identify the regional geological structures using the surface satellite data. From the satellite data, which gives an expression of the surface tectonics and the subsurface information from the tilt derivative. And we have superimposed, and we have seen that most of the areas along the Tista boundary, along the Tista fan boundary, the satellite derived structures and the gravity derived, like tilt derived structures, are in sync. So this is the regional extent of the tectonics as well as the structures derived from the satellite data as well as from the gravity. And then based on this, we have taken the boundary of Tista fan to do further do the field survey and gravity survey, GPR survey. So this area was being identified for for hotspot studies, and then you can see that in the fan region, the proximal and the distal fan are very can be well separated for this Vista fan region using the PC, the principal components of the Landsat data. And the field survey was done where in the proximal area the gravelly and the sand unsorted facies can be seen, whereas in the distal part it was a well established alluvial deposit was found where the agricultural area sustains. In the proximal area mostly it was a tea garden. And then we have carried out the GPR survey. GPR survey was done along the Mahananda river bank, where we could also identify some of the signatures of tectonics in form of abundant channel, then incised gully, then unpaired terraces. So all these field evidences were been identified in the Mahananda river bank, where we have done the GPR survey to understand the subsurface tectonic signatures. So this is the GPR profile. So we have seen that the subsurface and the shallow surface manifestations of the basement discontinuity was being observed within the depth of 1 to 2 kilometers in some of the areas. In this particular area where we have seen the surface signatures in the satellite data as well as in the field. So in the satellite data also we can have some of the observations where there is a indication of the structures controlling the paleo seepages or the river activity of a fluvial system. So all this cumulatively gives us an understanding that the geometry of the alluvial fan is considered to be controlled by the basement architecture. The satellite gravity-based basement depth and tail derivative can be used to estimate the sediment thickness and delineate the subsurface discontinuity in the alluvial system. And the manifestation of the major subsurface discontinuity can be interpreted by the optical and the SAR images in the form of major lineaments, as we do from the surface structures, identification of the surface structures. And within those areas where we have identified the subsurface discontinuities as well as the surface imprints, for those areas we have done the surveys and found that the signature, the shallow discontinuity is observed within the sediments using this GPR profile. So thus it tells us that the optical data combined with the gravity derivatives and the field survey can help us in understanding the morphology and the tectonic evolution of the major fan within the Indo-Gangetic basin. And the scope of study, extension of the study is also I will be emphasizing upon, because the entire Indo-Gangetic plain is not well studied. The shallow surface structures are very important as they really mold or change the morphology of the fan. So it can be studied the extent of the western Gangetic plain and the entire Gangetic plain can be studied using such kind of method or methodology. So I'm thanking you for all your kind attention.
Bangaru Babu, who has to complete his presentation.
Elevation is high elevation contours are located in western part. The eastern part is covered with coastal diagram. That's why we are getting the elevation contours here. So this is the Boger gravity map of the present study area. We have got the two gravity highs at the western and eastern part of the present study area. Western gravity high we are interpreted as a Uluru system. Because of schistose rocks we are getting the gravity high in the western part. Eastern part we are getting the gravity high, one is due to the eastern part mobile belt. Between these two gravity highs we are getting the one gravity low trending north-south direction. It is sandwiched between the two gravity highs. So we are mostly concentrated in this gravity load running several kilometers from north to south area. So we are taking this gravity low closures located in northern part of the area. Based upon the nature of signature and anomalous trend, we are interpreted the shallow part in this area. Apart coming to the southern part, we are brought the same signature. Two gravity laws are separated by some distance here. So based upon the superficial signature of this gravity laws, we are interpreted one more fault. So this gravity law, we are getting the granite gneiss between these two gravity lines. So we have conducted the same area which is covered by the magnetic survey. So we are getting the magnetic of 1000 nanotesla to minus 140 nanotesla. So magnetic did not give any significant result for this gravity law. So we are concentrated further gravity anomaly data for further interpretation purpose. So this is my general practice. We are superimposing the gravity, local gravity on the geological map. Most of the gravity contours are trending the regional trend of this present geological map. So we are getting the segments, thick segments covered. We are getting it is encoded by the fault here in the southern part of the area. For delineating of gravity low, we are applied the tilt derivative technique to the gravity database. So where we are going to propose the segmentary basin between the two gravity guys, we are getting the low tilt derivative. So for delineation of this gravity low, we are applied the gradient magnitude technique applied to the tilt derivative gravity data. So we are getting the linear trend. It is exactly coinciding with this gravity low. One more linear trend. Gravity linear trend is located in the eastern part of the area. This gravity linear trend is discontinued here. We have interpreted this linear discontinuity is a fault. One more fault in the northern part and the southern part of the area. So by concluding this gravity law, we are applied the regional residual gravity map for using the high pass filter technique. So we have got the gravity low in the central part. It will trending north-south directions. So after that, so I want to conclude this basinal structure is continuing deeper or not. We have applied the upward continuation technique. So we have applied this upward continuation technique at different stages: 1000 meter and 2000 meter, 4000 meter, and 6000 and 8000. Out of all the successive continuation of upward continuation, in this 1000 meter upward continuation, that the particular proposed basin is continued for some depth extension. If you go to deeper and deeper, this gravity loss is disappearing. Hence, we have concluded this whatever basin-like structure is not continued at deeper depth. It is located at the subsurface structure. Apart from this, Nellore system and Eastern Ghat is continued in all these stages of upward continuation. Hence, we have concluded that the NSP Nellore system is at a subsurface feature that is extending at a deeper level. So after that, we are taking the inversion technique for interpretation of the gravity profiles. We are taking the four successive gravity profiles perpendicular to the gravity trend. So we are going to invert that gravity profile, selected gravity profiles. So compact density inversion method is used to obtain the density structure of the aluminum sources lying below the subsurface. In this method, we are going to divide the several rectangular prisms of the uniform thickness density contrast we are taking. So we have prepared a 2D model here. So this is the profile, AB profile I am taking for inversion technique. So this is the gravity we are taking. So dotted one is observed and calculated. Apart from, we are taking the different derivative maps for the same profile. This is the elevation map. So we are inverted this particular gravity profile. So we have prepared one basin-like feature like this. This is the low density contrast material below this gravity low. So we are going to interpret this low is a groundwater segment. Eastern part is due to the coastal segments. So we have prepared a 2D plot for particular database. We are getting deeper depth at 6.2 kilometers. So this 6.2 is related to the Nellore system. We are planning this shallow depth is around 1.5 kilometers due to the groundwater basins. So these are the different models we have generated by using this inversion technique. This is model below the CD profile. So we are getting the same low contrast density material below this gravity low. So we are claiming this is the Gondwana sediments. Same, we have applied this EF profile also. So DF, we have got the one more GF, this is coastal sediments. So one more thing, this is one of the work is carried out by the NGRI. They are taking the seismic data from Kavali to Roorkee. So they have interpreted this deep seismic data from near to Kavali area. So they have interpreted Mineralogical system and Eastern Ghat, but they are claiming the Gondwana segments with a low velocity layer up to 1 kilometer. Fortunately, my area is falling in this area, it's a Kavali area. Yeah. They are claiming the Gondwana segments below 1 kilometer depth. So this is my profile. Fortunately, falling on the seismic profile here to previous study. So what we are depth calculator from gravity inversion is exactly coinciding with the seismic data set. So this is my proposal based upon the gravity data. This particular northern part is already delineated from the gravity and seismic studies. So now we are going to propose one more Gondwana basin below the southern part of this present study area. So it is more delineated by the further seismic data set.
Please come to.
These are my field photographs. So I thank HOD, DDG and HOD. I thank to Kavali Nellore, DDG Geophysics. I thank to AEG for giving the opportunity to share my work in front of this science community. Thank you, Madam.
Thank you very much.
We are in regional purpose, so we are mainly concentrating on gravity or spectrum. And if you are detailed mineral for mineral purpose, we are concentrating on magnetic.
So for mineral, we cannot take gravity also.
Gravity may mostly comprise of deeper information, and yeah, we can take that, but depend upon like objective of what is our.
I think during the tea time you can have a discussion.
Yes, okay.
Any other question? The speakers? So if you don't have any questions, so please, sir, please.
Swati, you have used different data sets for your studies and came out that the findings are similar. So do you optimize that in your next study, which you say that it can be extended to the different parts of the Himalayan region? Will you optimize your studies by using limited data sets, or you will prefer to use again all the data sets? Should be optimized.
Yes.
So which data set you will prefer?
Thank you for the question, sir. This study can be, we can further use this ER data also, sir, magnetic data in for this kind of study. But as of now, the resolution is not very much supportive. So if we get some ground data, ground geophysical data, we tried in the Bhukosh. So we did not find it for those areas. But definitely more data in terms of like optical, we are trying to integrate and identify the surface manifestation of the subsurface features and trying to relate it with the basement structures, and then going in deep and then doing the field surveys. So probably other data set, gravity, ground gravity and magnetic data set may further improve the results and findings in identifying the hotspots where the tectonics is more prevalent and where we can have the surface manifestation of the base. The basement structure is really contributing in the change in the morphology or of the fan or the like we know that in the Kosi region, the fan is being fluctuating, the morphology has been changing, the vista is very tectonically active fan. So all this has to be seen in a very localized as well as in the regional perspective. So I hope I am clear. Yes.
Well, this is not a question. It's only just a remark. Of course, if there is any other question from the audience, please. Any other question to any of the presenters today? Otherwise, I will go ahead with some remarks and some clarifications. say Dhami sir, I think from MECL, the kind of say well-log analysis integrated in a way to estimate the potash, okay, when estimation done. It's a very good thing. But to me it seems it's more like a textbook like what is that trend which is going to be different in the sense most of these things are known. Say for example you have got gamma ray, dual density, and you have perfectly used very nice. Okay? So I am just asking you, what is your contribution? What is the novelty of your work, which was not there for the benefit of audience?
I told initially they were doing only gamma,
Okay.
and they calculated huge reserves. They didn't differentiate between clay, gallugnatic and potash. But when we adopted spectral gamma, then we identified clay separately and then gallugnatic sandstone as well as potash mineral.
I have to agree because I mean these questions because whenever you try to present, you should have a slide on novel, okay, and you should quickly tell the audience what is your contribution, because otherwise I have to intervene, or a person like me have to intervene and bring out what is the importance of your work, okay, and especially there should be two slides. One is gaps in knowledge, the second one should be knowledge, so that you straight away bring out the things in focus. Okay, this is only small question, otherwise it's wonderful. The second thing, Bangaru Babu, and you have done the Kavali Nellore area and you concealed the east coast sedimentary basin. It's more of a regional type of okay? And how you think that it is going to fit into this ESRAJU? The theme of this particular conference is ESRAJU. So how you think that it will be wonderful?
Yeah, we are delineated basin like which are near to the surface. So 0 to 500 meter to 1 kilometer depth. So we are taking the inverse technique for interpretation of this gravity load. That's why I am applying this ESRAJU.
No problem. Yes, it is a good one. And subsequently, the specific one is being taken care of by NGRI. That is in goal. Okay. And coming to the work by V S RAJU, the multidisciplinary geophysical surveys. I mean, most of the time you have spent on 100 meters. Okay. We want results. Okay. And coming to the point that the chromite mineralization and in that particular region is highly tectonic environment. Okay, highly tectonic environment. Okay, and what is your experience in this? Because a message has to go to the audience.
Yeah, the slide which I have shown on the Sukinda, not concentrated on the Sukinda proper. That is the extension of the Sukinda belt that is towards further south. There is an area called Katpa. The main ore body of the Sukinda is already mined and the ore grades are reducing. Our aim in this particular study was to find out the extensions of the Sukinda chromite bodies using integrated geophysical surveys at a cost-effective analysis.
But gentlemen, the chromite, as you rightly said,
It's difficult.
on the basis of geophysics
Yes,
is a
that's,
highly difficult task.
I already expressed that.
Highly difficult task.
Yes.
Because we burnt our fingers.
In Katpa region, the advantage is we got 16 borehole controls, and we could able to
No, please
integrate.
don't take these remarks. It's only for the benefit of audience. Okay,
I expressed the difficulty in my talk itself, how difficult it is.
Okay, then thank you so much.
Thank
Okay,
you.
and next over to
Chairperson for the session, Dr. A.K. Chaturvedi and Dr. R.G. Sastri, to please come up on the stage and facilitate our authors.
V S RAJU, kindly step forward. Next is Dr. Dhami. Mr. Dhami, I'm sorry. Mr. Deepak Maurya. Dr. Bangaru Babu. Now I will request Dr. to please come up on the stage and facilitate our chairperson. Also, another announcement, we have posters installed at the back. Please have a look at those too. Thank you so much.